Okay, so looks like we're live now. Welcome to virtual JBug. This month we've got two talks on transactions in the cloud, and I'll go into some detail on those in a moment. But let me bring up my slides. Okay, so one of the first things you might notice that we've rebranded as Virtual JBug. We used to be JBug Worldwide. So we kind of switched the name because it was a bit of a mouthful, and it wasn't really obvious what the worldwide bit actually meant. So, and also people were calling it Virtual JBug anyway, without us telling them that that's what it was called. So, by popular demand, we've now switched to Virtual JBug or VJBug. It's also in line with the VJug, the Virtual Java User Group as well. What are we about? So we're doing a series of user group style sessions over Google Hangouts on air. We're trying to make them kind of fun and interactive rather than kind of dry webinar style talks. They're also kind of developer focused as well, so they should be of interest to developers. Of course, we're always interested in feedback, so just come to our meetup page and you can message us there, either publicly or privately, whichever you prefer. And there's the URL to the meetup group. So yeah, so today's sessions. So we've got two talks, both with a transactions and cloud theme. So the first talk is kind of more high level, and that's going to be talking about what provisions there is for transactions in NoSQL and how the different models work and what kind of scenarios that they're good for and what they're not so good for. So the idea here being is that if you've got an application, if you're an architect, you can kind of understand how your application would behave under the different types of transaction models. And the second talk is talking about how to scale a transaction manager in the cloud. So this is kind of a bit more low-level details. And here we're talking about how we can actually make a transaction manager distribute over a large cluster. The talks are by our two Red Hat summer interns. They're just coming towards the end of their project. One of the purposes of this talk is to for them to do a practice run before they do the real talk at university this Friday. So we really want to get some feedback. So after the talk, it'd be good if you could ask some questions, but also give feedback on maybe what slide you didn't quite understand, how they could improve the slides. Also, to make it a good trial run, we're going to be quite strict on the time. So they have 25 minutes to do the talk for real. So we're going to start the timer and we're going to let them run through for 25 minutes before we ask any questions or give any feedback. So just kind of keep it in your head as you're going through. And then we'll have about 15 minutes or so to provide feedback afterwards, maybe 15, 20 minutes. Also, if you're watching live and you're not too interested in the feedback aspect, then I'll let you know when we finish what time we'll be coming back on for the second talk, so you can tune back in then. Okay. And of course, if you're watching remotely, then yeah, if you're watching live, then feedback would be great. If you're watching the recording, then feedback probably is only valid until this coming Friday. Okay, so what sessions have we got coming up? We've actually got another session on later today. That is the wrong time. Good job I spotted that. So our next talk is on this evening, and this is coming live from the Boston Jug in the US, hence the late time for those in the UK. It's on Java and so Java SE and Java E, hands-on rapid Java EE7 development. So basically, Andrew Rubinger is going to be talking about some examples from his continuous delivery book that he's just published with O'Reilly. We also have a guy from Zero Turnaround called Adam Bine, and he'll be using the JRebel tool to show how you can, at runtime, modify the code without having to redeploy it and rebuild it. So they kind of complement each other. So when your test fails, you can fix the test and rerun it without having to recompile and redeploy everything. We also have another testing themed talk in October, and on October 21st. And here, Aslak Knudsen will be talking about Archillion. So that's the his project on testing with inside the application server, so running unit tests inside the app server. He also co-authored the Continuous Enterprise Delivery book with Andrew Rubinger, who's doing today's talk. We've also got some other talks that are to be announced. They're not confirmed yet, that's why I haven't put them on the meetup page, but I'm hoping to get those confirmed in the next few days. So just keep your eye out on the meetup page. Okay, so Adam Bien is not the person who's doing the talk tonight. He's the person who's doing the virtual jug session. So, a bit of a mistake there. So, coming up, there's also a virtual jug user group, which is similar to the virtual JBug user group, but focused on Java, and it's not run by us, it's run by Zero Turnaround. And you'll see their meetup page at the top there as well. So the next talk is on August the 27th, and Adam Bien is going to be talking about Java FX in version 8. And then the next talk is on September the 2nd on pragmatic functional refactoring with Java 8. So this talk sounds quite interesting, actually. So with the recent addition of functional programming to Java 8, this talk's going to talk about how you can refactor your existing code to start making use of the new features, the new functional way of writing applications. So it could be a good talk. Okay, so that's the end of what I had to say. So Testing, testing, testing. Testing, testing, testing. That's fine. Testing, testing, testing. Testing, testing, testing. Testing, testing. Testing, testing. Okay, blah, blah. It's very quiet. Okay. Testing, testing. Well, okay. Sorry about that. It's either working or isn't working, so. Sorry.
You can try shouting. So in a compensating transaction, you've got two stages. You've got the first phase, which is like 2PC. You've got all your commits or your updates. In the second stage, you've got your commits or rollbacks, basically. But because we're doing single updates, it means that there's no locking on the whole transaction. The only locking is the atomic locks when it updates those single records. So that means that the throughput and the contention is relaxed a little bit, so that you won't get the failures that we saw earlier, because both of these can update at the same time. It does mean that the isolations can relax, so they're always visible. So the emphasis is probably more on the business logic, and you want to so to do the experiment, I looked at, I think, 70 plus different databases to run the experiment, but I found that TokuMX, which is a build on Mongo, was the one that offered ACID transactions in pessimistic mode and optimistic mode, which gave me the most flexibility for doing a wider range of tests. It's a document store and it shards, but not transactionally. So that was something I had to deal with later. So my experiments were broken into a group of scenarios that I set up. So I set some scenarios sort of in my mind of what a typical workload might be. So I thought that loggers, analytics machines, maybe an online retailer, a balance transfer, what happens in the bank. Tried to come up with workloads that would maybe mimic real life to some extent. I mean, they may be a little extreme, the ones I do, but you get the idea. And the tests. So I did tests for transactions, no transactions firstly. So just seeing what plain old Mongo calls did, basically. I then compared them to pessimistic transactions, and I was unable to use optimistic in most of the tests for TokuMX because of the way they commit. I'll come to that in a bit. So my third test is using an MVCC transaction with a pessimistic to come up with their advised, Toku's advised sort of model for making a transaction. And then I used to compensate transactions. So each experiment, I basically set a number of parameters to each run, so that I could say run in this mode with that percentage of a read chance. So I set the read chance, which states how likely a process is to read, write chance, how likely something is to write, insert, same as above. The transaction size states how many records within each transaction that a transaction will hit. So if I've got a transaction size of 3, that means I will hit 3 reads potentially, or 3 inserts, or 3 updates, whatever. The wait time is how many seconds or milliseconds between each action that I can wait. So if I wanted to model a user doing input, I might want a longer wait time between transactions to mimic them looking at a web page and browsing around a little bit. The records is how many records are in the data set. So to encourage high contention, I could really slim down the number of records in my data set, or I could, go for thousands and thousands. Thread count, how many threads are running the process, and the time to run is just how long the transactions ran for, or the process in total ran for. So generally I went for about 10 minutes because I found that was the level where I could get a lot of tests done, but I was getting fairly good results. So as I quickly said earlier, TokuMX has an issue with the way it does optimistic transactions. So it's MVCC. It doesn't. Well, what's the best way of putting this? It doesn't take into consideration updates that happen before it completes. So if you have two processes, P1 and P2 take the same snapshot. One does a large set of work, and as you can see, P2 does a slightly smaller set of work. So P2 finishes first and commits its work. So normally we would expect the process with the longer amount of work to realize there's been an update and not do anything, to roll back. But in Toku, they haven't written it to take any consideration about that whatsoever. So it will overwrite whatever you've got there. They've written, I think, the idea behind it is that it's really good for reading. They really want you to have a good read transaction, but they don't care about the MVCC writing at all. So that was a really interesting issue to come across with me. Right, so now I'll go into the experiments and the results I got. So my first scenario, which is a log, I set it up to be quite read heavy. So I set collection insert heavy, so the insert chance is 99.9%, and then it's 0.1% for a reader. Because it's inserting only, there's no point in having any records there initially. And basically what I found was that, as expected, standard no transactional Toku works the quickest. So that's just doing atomic updates on single records is by far the quickest. Pessimistic and my mixed transactions are fairly similar. This is probably because both of them use the same sort of serializable locking mechanism when they come to write. But my compensating transactions, in this case, are really low. I can't remember how slow they are, but I mean they're like 67 calls per second are running through. So this is over 6,000. These are around 4,000, 5,000 calls per second. Compensating transaction has a really low rate, and that's probably because these three are just doing one insert, and that's all they do. The compensating transaction, though, does an insert, and then when it comes to the second phase of compensation, it does an update, and the updates seem to really slow it all down. So that's where you could have run. Well, I could have run a compensation in a slightly different way, and maybe used it in a slightly lazy way, where I did the second stage in quiet time, in which case you would sort of see that sort of throughput on the first initial insert phase, and then the second phase you could do, in your own time when it's quiet, when there's nothing much going on in the system. My second scenario isn't insert heavy, but it's update heavy. It's almost the same as the first scenario, but instead of inserting, we're just doing updates. And as you can see, all of them are a lot slower than the first scenario when it's updating. So it's kind of in tune with what we saw in the first slide with TokuMX being quite slow. So the parameters on this one, I've set the record count to about 450. The update chance is 99.9, read chance is 0.1, and the transaction size is 3, exactly 3 each time. And yeah, so no transactions again perform best. That's the theme we'll keep seeing that no transaction is by far the best. Pessimistic and mixed is similar. This is because, again, both of them use the same sort of serializable lock when they come to write in an update, and because we're very update heavy, they're going to be the same. But compensating transactions, even though we're doing both the initial update and then the compensation at the end, it's still quicker than both of these because it's not hitting as much. Yeah.
You had a compensating transaction like approach, let's say.
Yeah.
That work on stock Mongo, but it doesn't have to be the top two.
Yeah, it's fine. It's fine.
It's just the two in the middle that are top two. The two on the outside, stock Mongo, salt top, but ran on top.
Yeah, so yeah, it's all running. Yeah, so it's all running Taco, but you could do it in Mongo if you wish.
Taco is also tuned quite heavily out of the box, whereas Mongo isn't much. So it would be unfair. Yeah, it could be ran on Mongo. You would get worse results probably if you use it on Taco.
Mongo like it's been Taco and get those certain things.
Yeah.
I'm not sure if there'd be. It's quite tuned, so it would have been really good if I could have done a Mongo section and a Taco section, but changing the two is quite a challenge. You know, to do quick tests, it was much lighter just to stick with Taco and do all the tests on that.
I guess I'm just trying to like ascertain that the compensating transaction doesn't rely on anything.
Oh no, yeah. Oh yeah. So the mixed and the mixed and the pessimistic are Taku elements of Mongo, whereas the compensation is just a model that you use. So onto my scenario 3, and this one I kind of have developed to be one that you wouldn't necessarily think of to use. Maybe. So it's a really heavy online retailer. You've got 450 records, 99% chance of reading. So this is really like the users interacting with some data. And then an update chance of 0.1%. Transaction sizes of 1 to 10, and a maximum wait time between actions of up to 2 seconds. So you get quite a long wait between each action potentially. So I mean, if we had 10 transactions and they all took 2 seconds, it's going to take 20 seconds to do that one transaction. So that's quite a lengthy transaction. What I found was all of them perform quite well, bar the pessimistic transactions, because the pessimists, they need a lock. You know, on everything they do, they need a lock. So you have a lock on the read, you have a lock on the write. Because there's so many reads going on, and the transactions are so big, the pessimistic really struggle. Whereas the optimistic and the normal and the compensation, because they don't place locks, they just take it. Mix, for example, just takes a snapshot. The other two don't care. It's quite lightweight, and they all run through at exactly the same speed. I'm not sure why that's not higher, because they're all running through at 58 calls per second. So that's something wrong with my slide. The pessimistic had huge failure rates. So you're talking like 98% failure rates on reading and 96 on writing. So it's really high. In scenario 4, I set this up to be a bit more of like an auction house type thing. So again, 450 records. I thought that was a good level of contention for this. The read chance it's more of a read bias, so it's about 70%, and the update chance is 30%. The transactions are a bit smaller, and there's a lot less weighting between each individual action. So again, as you'll get the idea, is no transactions work by far the quickest. Pessimistic and mixed transactions, again, because mixed isn't a true MVCC, it's not truly optimistic, it's using a serializable connection that is essentially the same as the pessimistic. They're very similar results. Whereas the compensation transaction is around about half. I think it was maybe 1 or 2 less than half. So it's pretty much up there, and this is guaranteeing that it's stored within a transaction, whereas this one, there's no transaction whatsoever. In scenario 5, which is a 50-50 read-write balance, is a bank transfer. So this one I did slightly differently, the test. So instead of just a plain old update where I'm updating a single record at a time with a random value, in this one I want to take value from one account and place it on another. And I want to make sure that I'm not losing money or funds in between. So we can see that straight away no transaction is really quick, but there's absolutely no guarantee that the money you're left with at the end of the process is what you started out with. And if you you can force errors, and if I did force errors, you could see the balance of the whole system just spiraling out of control. So again, yeah, no transaction is best, but you don't have any control over what you see. Mixed transactions and pessimistic were both struggling a bit with it. And then the compensating transaction, again, is just a lot quicker because it's not placing so many locks. It's just one lock at a time instead of a whole batch of locks over the system. And again, I used this I did the initial update and the compensation in one action. Again, I could have broken that up, and I think I would have got the same sort of update rate as that, and then I could have done the compensation in my own time. But I did both in this action. And then to quickly summarize, I found that no transaction model works best in everything, unless you want to have some sort of guarantee that what you're putting in the system is what you mean to put in the system, which is kind of obvious. The no transaction model obviously makes no guarantees. Optimistic transactions I found really good for reading, but I wasn't able to properly test them in Toku because of the fact that they don't support them properly. And ACID transactions both seem to really struggle in highly contented data, whereas the compensation relaxes the contention essentially by breaking up the transaction into smaller stages and giving you less isolation. But yeah, it increases their throughput. And then, what I probably should have said about compensating transactions earlier is that they allow you to place more emphasis on business logic. So, when you're updating records, you can use it like a flight recording, a booking system as an example, I suppose, where if you overbook slightly, the compensation stage can be handled by business logic, and you could upgrade the person who overbooked, or you could move them to a different flight, or you can handle it in the business logic. Whereas in an ACID transaction, it's just you failed or you've succeeded. There's no space to handle that. And in my future work would be to shard it. That was to be my next stage is to shard the transactions and see how they scale. I imagine the computations will shard really well. And obviously I can't shard the rest in Toku, so I'd have to find something else. But yeah, that's it. So if there's any questions, I'm not sure what I did for time on that. Was
pretty good. You're on 25 minutes, but
30 minutes of sound check on the questions.
Okay.
Lots of the questions for about 2 minutes as well, so you've probably got about an extra 5 minutes.
Okay, wow.
Which is a few things I think, I guess,
yeah.
with the feedback we'll probably get an idea of what you can spend the time on.
Why do you think compensation transactions do really well on sharded and said you've got some context?
Sorry, yeah, I could probably explain. I'll go back to that one. In a normal transaction, they don't tend to scale so well because, certainly in a pessimistic way, because the transaction needs to hold the locks on all of these. And so holding locks distributed in a distributed way is pretty tough. You know, if you've got a lock, you know, you've got records all over the spot, then it's very difficult. So they generally don't shard very well. Whereas in compensation, because we're only locking one record at a time, as we do the atomic update, you don't have that same lock problem. If you see.
But if you shard the data, can't you just shard the locks as well? So you don't need to have distributed locks.
I don't know. To be honest, we don't know that one.
So how do you think that would work?
Well, if you've got all the data for the criteria on a particular node, all the locks for that data on that particular node as well.
I think I'm not sure I'm following you, Stuart, but I think essentially the problem is, you know, it's the same like when you've got a two-phase grid and multiple databases. You've got like lots and lots of databases. It's, you know, it's two-phase coming over many databases is going to be slower than over a single one because you've got lots of network calls and so on. So I think it's the same issue. If you've got your data spread over lots of machines, cluster, you know, if you kind of, you know, you're looking at data item over here, and then you need to do a remote contact some data on a different shard and then a different one.
It will scale with the number of data items you've touched, not with the whole size.
It should. I think it will scale providing you only touch data within the same shard, within the same transaction. Because then essentially sharding in that case is just kind of reducing the amount of data, putting it somewhere else, isn't it? Yeah. So I think in that case it would. But if you have to touch data in over many shards, I think that's when you're going to get the distributed transaction problem slowing down. And you also hit issues around cap theorem as well. I don't know if does that answer your question, or I'm not quite sure if I understood your question properly. If it answered it, then great.
I suspect that if your lock store is distributed with your shards associated strongly, then you don't get quite many problems.
Yes, I think so in that case, your data would have to all, if everything was all on the same shard, the locks, all the data that you were updating, then it would work fine, is what you're saying, which I agree, it would do. I think the problem comes when it's spreading over multiple.
Possible to show scenario 3, please?
Yes.
I'm confused by that. Did you try running with 100% read?
Yes, I don't have the.
Did you sort of the same? Because I would have thought if it's only read operations, you shouldn't be requiring a write lock or the exclusive lock on the data. It should only be requiring a shareable lock.
Which one are you talking about?
Yes, the pessimistic.
In Toku, everything does. So the read operation takes a lock, and it will lock until the end of the transaction.
It takes a write lock, but
it takes a write lock. Yeah.
Even for a read.
But yeah, basically, I think the idea behind it is that there's a bit of a gap in the way they lock in Toku. So basically, you take a lock on the first, maybe it's easier to find a slide with. So in Toku, what happens is you take a lock on that first one when you read.
You take an exclusive lock.
Yeah, so nothing else can read, see what's happening there. They completely lock that. And I think the idea is that if you do a bunch of reads, you can lock all the records you want, and then you can come and do work on that.
Right.
So I think that's the idea behind that. Because if you weren't to do that, if you were to lock one record, do some work, lock another record, do some work, you would sort of build up your locks in the work, but you couldn't guarantee that the first record had done the same thing as the last record.
So they don't have the kind of ramp up two-phase commits. They actually acquire exclusive locks straight away to get very steep.
Yeah.
Right. So it doesn't sound like you've picked actually good to get optimistic locking wrong.
Yeah.
And the pessimistic locking is not optimized.
Right.
it's quite difficult to figure out exactly what to examine.
Yeah.
To be answering this, sorry.
I mean, it took me a while to find the bit in the documents where it says MVCC operations shouldn't be used for writing, and it's literally that line in 1,000 pages of document.
Yeah.
And then when I spoke to the guys, I haven't been able to actually work out what the intention was behind it. So I sent a few posts off to a few different people and workers. No one really came back with a sensible reason for wanting the MVCC transactions to ignore what happened. I imagine it's to do with throughput, and they just want a quick way of reading. But
they want a consistent read, so you get a snapshot of read, but they haven't implemented yet. The support for writes, I don't know. It's quite new.
If they say it's pessimistic locking, optimistic locking, it should still maintain consistency.
I know. I know. I think one of the issues there is very difficult. So Sam did a review at the start, and we just had to. It was quite cloudy. Excuse the pun, on which one to use, and we just had to make a decision based on what it looked like that they did. It's not until you kind of get into it, when you start seeing weird behaviour and investigate it, you realise what the problem is. So unfortunately, you just have to be pragmatic and have more time and investigate more. But I think Sam looked at some like Foundation DB as well, and that was doing slightly different.
That
wasn't quite
that was just doing it in an optimistic way. It would be really good if Foundation DB had done.
So they didn't do pessimistic, did they?
Pessimistic, but they don't do that at all, and they don't do just plain calls. So like, you've got a sort of trigger way of doing a plain call, so you've got to do individual transactions to mimic doing just atomic updates, which, so there's a lot of overhead in just mimicking the system on a basic level. So it was much easier from the outset just to go for talking, which seemed like it was going to be, the answer.
Sorry, it's not clear what's the maximum concurrency you will get, like how many operations we're trying to update the database.
Oh, sorry, I was thinking 150, it was running over 150 concurrents.
So what does MVCC concept stand mean? Something related.
So it's just optimistic basically, so it just takes a snapshot at the start here, and then the transactions run through, they do their work. At the end of the process, they check the snapshot. If it's changed, then they roll back. If it hasn't changed, then they commit. So it's just
if you go back to the graph, was it the third one anyway? But there's the read one, and then the update. The graph.
So about scenarios.
Yeah. So that's the read heading. What about the update one? I don't understand why the read one is like worse than the update one for pessimistic transaction.
The implementation is broken.
But it sounds like there's one type of lock in this thing. And so why wouldn't they get the same performance? Why is read worse than update?
I think the difference between the two might be.
Well, this one's insert, so I can understand there's no context.
Sorry, that's a typo. That's a typo on my part.
So this one's an update. So you're getting like 50 updates with pessimistic transactions, but you're getting like one. So it's blind reading slower than updates. I don't understand.
So you're between this one and that one?
Yeah, and just on the red column.
Okay.
Why do you get more updates than that?
So the key in this one is the length in time at which how long the transactions take. So in this one,
I was going to ask at the time when you presented this information, have you got a graph with this with maximum weight of 0?
No.
Okay. So I guess those get more. Obviously, they're going to get more throughput, aren't they? Because that's got an artificial sleep in it.
Exactly. So I could have done. I had to weigh up between doing, hundreds and hundreds and hundreds of tests, and I think I've done 25 that I got here, and I've done probably about 75 more. So it's sort of.
I suppose it doesn't matter to that specific test data. It doesn't matter about whether you did the sleep or not, or when I'm comparing it to the other one that hasn't got a sleep.
Yeah.
I'm starting to think, well, it's getting more updates than reads, and that doesn't make sense.
Yeah, yeah,
But that's because it's just got the zero sleep.
Exactly.
Non-existent sleep.
exactly. Yeah.
Okay, so we need to kind of press on. So we've got like 5 minutes left. So it'd be good if we could get some kind of feedback on bits that didn't make sense to you or things.
Well, I spelled that out because it needed clear.
Yeah.
They made clear to know why
Okay.
it's the more updates, and I understand it now.
Yeah, MVCC also was hazy on that.
Right, so you didn't understand, and did you understand what they meant by compensated transaction, how it works?
Yeah.
No, it's just
If you just, if you point out that it's just basically optimistic.
Okay, right, yeah.
And I would have completely understood it, so.
Yeah, it's probably just, I didn't even realise I got MVCC in there. I'd probably just blurt it out without realising.
Yeah, can I point one out on presentation slides as well?
Yeah.
It seems when you're less confident about what you're saying, you start looking at the ceiling, you look at the floor, you look at the slides. When you're confident, that's when, as well as the slides, you start looking at the audience.
Okay, right. I think that's probably.
So be more confident. That's what
I think that's probably to do with like memorising what's on the slides and maybe not the yeah.
No, don't be more confident, just bluff when you're not.
Yeah, exactly. Yeah.
That's what you need to do.
So I'm not convinced it's actually worth explaining MVCC.
Sorry?
Yeah, just leave the word out entirely. And don't-
Yeah, I tried.
Do you just talk about how they do optimistic, rather than mention the
Well,
MVCC
MVCC is only interested in the readers that report rates and vice versa, but this value is an exclusive report to be
Yeah.
Okay, relevant.
Would you still refer to it as an optimistic transaction versus pessimistic, or would you use some other way of describing it? Or you need some, need some snappy term to use to refer to it.
Why do you need to refer to it at all?
Well, because it's in the.
Well, you call it
What does it change the? Oh, I see. You've got mixed.
Mixed, so by mixed, I probably mean their advised model, I suppose. The Toku's advised model of how to use a transaction, or to use the transactions.
Your intention was to test optimistic lock-in, but obviously you didn't manage that because the middleware didn't provide it. And so.
The data store didn't provide it.
Yeah. Storage, yeah.
Yeah.
Don't blame the middleware. That's us.
And also, I'd be careful, well, not careful, but you did refer to no transaction as the best a couple of times, and it's not the best.
Yeah.
In all circumstances, it performs the best.
Yeah, yeah.
But you've got to be really careful. You said, of course, no transaction is best, of course, and you know, that's not the best way to think.
I think
that's that information.
I think one of the things you discovered that transactions don't perform as badly. People seem to think that they do.
Yeah.
And there is a cost, but of course there is because you get extra guarantees.
Yeah, exactly. And that came out over the presentation, but sometimes you were contradicting yourself by saying it was the best.
Yeah. So it's the fastest. It's got the highest throughput, but you lose all your transactional guarantees. Yeah.
One of the things that puzzled me was he said none of the methods suffered any failures, which sort of implies that no transactions work just as well in this scenario.
So in my scenarios, the no transactions didn't. What I maybe should have said is the no transactions. They didn't hit any lock failures. So the failures are lock failures. I should probably clarify that.
Yeah, because that implies that they just
There
go
are
straight
business
through.
logic failures because I presume the account balance was all over the shop on the no transaction update one. I presume.
Only when you don't. If I was to include like artificial failures, yeah, or if I was to reduce.
So record size down.
Yeah, what I did to force errors was to reduce the amount of time locks could wait for, because in pessimistic you sort of wait for a lock to occur, so you could wait up to like 4 seconds, a minute, whatever for a lock. But if you reduce that right down, you force errors, so you force lock errors, and when you do that, you can really see how badly it performs and how the guarantees work on the others, which will not produce any difference in balance. Even if they fail, they don't produce balance errors.
Any other feedback?
So just thinking of the scenarios, maybe I might have got this wrong, but you're comparing update heavy with read heavy ones. but on your slides it says that the transaction size changes between the two.
Yeah.
Would it not be more beneficial if you're doing a comparison to have the transaction size the same for both graphs?
Well, it was one of those. I could have done the same model all the way across. Then I wanted to sort of emulate different types of workload rather than compare the scenarios.
Yeah. So, I'm sorry, I understand the different workloads, but when if you're comparing the read and update form, surely the transaction size should be the same.
Okay.
And then it should be, you would call it a new scenario when you change the maximum weight and things as well. Just because otherwise you're comparing different things.
Okay, right.
I think there's two things here. One is that the idea was kind of to come up with different scenarios so that somebody could relate to one of them. Let's say, so, oh, that looks most like my application. Once you've identified that, then you're comparing the apples to apples for each of the different transaction types. Once you've identified your application, the next question is what type of transaction should I use? So then you're comparing apples to apples, whereas you wouldn't necessarily say, I'm comparing, I've got, I'm not even sure how to explain it, but an application that looks a bit like an auction site and one that looks a bit like a logging system, you would never, I don't see why you would compare those two together. It's like comparing apples and oranges.
I think it's just the way the data is like, how the presenter didn't clarify that, because we already know that you can't compare the two, because one's got a sleep.
Yeah.
So it's just a way to present
it's
it,
just
so that people don't think that you can compare the graphs.
Maybe
there are definite unique use cases.
Yeah. So what? Maybe if I had a slide in between each.
I'll just say the words. People could, if you don't say the words, people might infer that you can compare the graphs.
Okay, right.
Between the two, and you can't.
You need to explain how to consume the data,
Yeah.
how you intend someone to consume this data.
But I wouldn't have a slide.
No.
Fair enough. Thank you.
Go back to the slide with the aims on.
I got a bit lost when I should have just said it.
Well done.
So my concern with this presentation is what we're presenting is deliverable to Red Hat's customers.
Okay.
What you're not presenting is what you as a student got out of this experience, or what value you added to us as a company, as an industrial sponsor. So you focused almost exclusively on the results of the first bit of that day. You haven't said anything about this tool. Is this an open source tool? Is this something our customers can take and run their own tests with? You said it's easily extensible. You haven't shown any evidence of that. You said you surveyed 70 odd databases. I've seen results from one. Where's the 69?
Okay.
You mentioned this tool's reliable. Where's the evidence for that? Is it completely automated? How often did it crash? Right. If you're not going to talk about it, take it off the aims.
Okay.
Otherwise, you're giving the markers ammunition to pick up on things and say,
Yeah.
you called this one out. Tell me more about it.
Yeah, the things you've got an extra, you were under by about 5 minutes.
Yeah.
So you have, I think what Jonathan said, there is actually, I think you've got quite a lot to talk about on those things. But the idea with the tool, we were saying that future work with the tool, an architect could go plug in their own numbers, and could go off and you could have like on an OpenShift, for example, you could go plug in your profile of your application and go off and simulate it, come back with some figures and tell you how the different transactions flow.
That's what we need to hear in the presentation.
So we want to hear something about the design of this tool.
Okay.
Something about how this is benefiting Red Hat. So you could talk about, follow these numbers, and Red Hat could maybe do a white paper to show their customers, whatever. I think compensating transactions, the angles play up there, right? Because it's not coming across in this presentation. Compensating transactions are really our thing.
Yeah. Okay.
They're not talking.
Yeah.
They're Red Hat thing. So this could be, one of the aims here was to show in what circumstances is Red Hat's compensating transaction product.
So straight through that, didn't it? Yeah, I think that would definitely be worth. I was kind of, I think from the sharding side, if you could say more on the sharding as well. I think.
Yeah.
I guess you haven't got any results there. So.
I think I went a bit quicker than I did in my dry runs, so sort of. got about 25 minutes worth of stuff when I do it by myself, but in front of everyone, it's probably sped through and put things together.
Yeah, I think we need to push on.
One very quick thing is Paul Ezel shelving marketing your thing at all? As if he is put slide numbers on, or you'll just get 5 minutes of him there.
Yeah.
Not worth it.
Alright. Thank you very much, Simon.
Thank you.
We've got various other, various other people's presentations. Luckily, I didn't finish. Yeah.
So,
yeah.
1 and 2.
Yeah. Just have time to
Just give us a second, let me switch things around over here. Go, ready when you are.
You just have down to shift the slides or not?
No, Simon.
Okay.
Yeah, I think so. I think it's up or left, go back and down or right.
Okay, yeah, there we go.
Yeah.
Awesome. Okay, in that case, I'll introduce myself. My name's James, and like Simon, I've been interning here for the summer, and over the next 25 minutes, hopefully, fingers crossed, you'll see the fruits of my labour. Okay, so quick look at what we're going to see today. We're going to have a quick run through of why I've done what I've done. We're going to have a little bit of I think about exactly what a transaction log is, and to talk about some of the existing transaction logs that are around and about. And then I'm going to have a little look at some of the middleware that I was using, which is Infinispan, and have a look at some of my benchmarking results and conclusions. So the motivation for this is that cloud deployments are becoming a lot more common. Many more people are wanting to use them, but the cloud environment can be somewhat hostile in that the VMs that are used tend to sort of come and go as they please. Whether you don't need them anymore, they might go away, they might fail, go away, and then be replaced elsewhere. And there's they don't provide any particular guarantees that your disk writes will survive this process or what have you. So we're looking for a way of removing any state in the transaction manager from away from the host and keeping it all together. Try again. Sorry, I tripped over what I was saying there. We're trying to remove the state of a transaction manager from the host that it's existing in. Okay, so the transaction log is just simply a record of where we got where we got to in a transaction. It exists to allow a transaction manager to recover from a failure of some description, which means it has to be failure proof, predictably. Traditionally, it's written to the local file system. Hence, if you lose the disk, you lose the log, and that's bad. Get problems. Typically, it would bottleneck a transaction manager. So, fingers crossed, what we're going to be seeing today will alleviate that bottleneck somewhat and allow a little bit of a faster throughput. And again. There we go. I think that'll do for that. I've run out of my notes there. Okay, so the existing implementations. The default implementation just writes to the file system. It writes a separate file for every single transaction going, and sort of scatters them happily all over the disk as is the behaviour. This can be a little bit slow because it has to write new file for every single transaction, remove it at the end of the transaction, etc., etc. So a way of speeding that up would be to write a continually
appending file or a journaling file on the disk, which is our second lovely little hard disk clip out there. Which works, yeah, somewhat faster. Still relies on the disk write, and it doesn't allow a random access to read the log. So with our original implementation, we can just, when we want to read the log, we can just call a directory listing, which is relatively easy. Whereas with our journaling store, we have to replay the events through the file. Alternatively, we could store it, or we could store the transaction log within the database, which is our JDBC store here, which is great because that removes it away from the disk. Hopefully, what I've done will improve a little bit in the performance of what that will offer, though, on account of it'll still have to write to a disk, and I'm hoping to remove that stage and just go for network writes. So we'll see that in a minute. And the last implementation is our volatile store, which literally just writes the transaction log to a hash map. So it doesn't provide any kind of persistence or what have you. It's not there for production use or to enforce acidic properties. It's there really for benchmark testing, and it provides a good indication of what the transaction manager can do without the bottleneck of the log. Okay, so our secondary design objectives, we want to be able to at least compete with the throughput that the other stores offer. Ideally, it would be lovely if we could beat it, but I think competing with it is fairly important. And again, the availability needs to not suffer, because at the end of the day, we're looking to try and build something that's better than we've got already. If we're building something that's worse, we might as well just use what we've got already. So, yep, there we go on that. Okay, so we've looked at lots of different middlewares to try and replicate our transaction log out across the cloud cluster. We've looked at the likes of JGroups, memcached particularly, but we eventually settled on using Infinispan, largely because memcached doesn't offer any kind of replication across its cluster. And although JGroups does offer a couple of classes that will perform that, it says quite clearly in the docs that these aren't well tested or rigorously tested classes in any way, whereas Infinispan does. And not only that, Infinispan uses JGroups as its underlying messaging service, so it would sort of appear to me to be trying to re-implement Infinispan to build the product out of JGroups. Seems like a lot of unnecessary hard work, really. Okay, so Infinispan creates a key value cache store across nodes that are connected to a cluster. It handles all the difficult stuff, such as a node joining, leaving a cluster for whatever reason for us. It provides a lovely little map-like interface. In fact, in the docs it says it even implements concurrent map, but I'm not convinced that all the method implementations in all cases are quite bulletproof. Yep, any key that's put into the cache is retrievable from any other node on the cache. It won't necessarily be stored on that node. And it offers several different modes of caching, of which two I think are particularly interesting to us.
Just because it's come to my mind, you said you're not convinced that concurrent hash map, and it's kind of implements all the methods correct, like, is it worth pointing out why you think that's best?
Yeah, probably. Sorry, I should have said so. So concurrent cache map includes the method keyset, which should return all the keys in the map. Infinispan will, when you call keyset, will only return the keys on the node on which it's called. So, in fact, to use my diagram for a different example, if I called this on node 3 here, I would only get key red, white, and blue. It wouldn't tell me anything about yellow or green, even though that they are in the cache, and I could access yellow and green through node 3. Just keyset won't tell me about them. Okay, so two different caching modes which are quite interesting. We have a distributed cache and a replicated cache. The distributed cache distributes the keys across the cache. You can configure how many copies of each key you want to keep. So you could keep, I suppose, minimum 1, maximum to your cluster size. So in my example here, I've kept two copies of each key, and they're sort of spread out over the whole of the cache. The replicating mode keeps a copy of every single key on every single node in the cache. And again, it can be configured so that when a node joins the cache, it will learn all of the keys that already exist. Won't do that by default, but a fairly easy configuration sets it up to do that. So in theory, in replicated mode, the key set that we were talking about earlier should work. Okay, so there's a couple of little implementation difficulties to overcome when using InfiniSpan. One is that it won't tell you how many replicas it writes when it writes to the cache. So, for example, I might want to guarantee my user that whenever he writes to my object store, there will be at least 5 replicas of his data, meaning that he can lose 4 of the 4 nodes and his data is still safe. However, with the InfiniSpan contract, if my cluster is below that size of 5, it won't tell me, or it won't throw any particular problems. It will just carry on writing to it quite happily. What InfiniSpan will do is, if the cluster size can cope with the number of replicas that I want, and it has any problems writing, it'll inform me about that, but it won't inform me if the cluster size is smaller than the number of replicas that I've asked for. Okay, so what we can do about that is call a method called locate, which is buried deep in the API and took some serious finding, and all that does is return a list to me of where where the key that I've asked it to be called is held. So on my previous example, go back one. If I called locate on red, it would give me the, I'm going to call them 1 and 3, but the top left and the bottom left there, for example. So all I do is call locate, take the size of it, and essentially if that number isn't big enough, I try the put again for a predetermined timeout. If it reaches the timeout and still hasn't managed to make the put, it removes the key from the store and throws an exception, causing the transaction manager to roll back. Okay, key set again, as we said, doesn't necessarily return all the keys in the cache, which means that when it comes to recovering, it comes to reading the keys, we need to know what keys are going to be in there in advance, which makes it very difficult to use something like a UID as the key. So what we do about that is make each key a number between 1 and an arbitrary number, 1024 for example, append the transaction manager ID to the front of that, and then just simply ask the object store, do you contain transaction manager ID, and then number what have you. And whilst running, the object store will keep track of which numbers it's allocated and which ones it hasn't, just simply through a Boolean array. And it will assume that if the array index is set to true, that number's been allocated and can't be given out again. Okay, so a good part would be to know how fast an object store based in InfiniSpan can work. So we've done some benchmarking. As what I'm trying to measure is how fast the object store can run, and as transactions will only write a transaction log if they choose to commit. I need an environment in which every transaction will commit, otherwise we're not really testing the object store. One could be committing more transactions and so appear to be running slower or what have you. Secondly, I'm not trying to measure into this any speed or what have you related to resource manager or any calls needed for that. So I'm just running dummy transactions that always commit and don't actually do anything when they do commit. However, they still do need to write to an object store in terms of UID and all the rest of it. So my job is to find begin a transaction, enlist 2 dummy resources, and then commit a transaction. And the benchmark test is to see how many transactions of this type can be pushed through the object store in a certain amount of time. And we've got some results here. So these results are taken on an average, or 5 runs of 10 minutes were made, and the results here are the average taken. As we can see, using a distributed store runs considerably faster than anything else, but even the replicated store keeps up with the journaling store, and our default file system store is, as predicted, pretty much the slowest. Volatile store I haven't included on that graph because it's just ridiculous. It's sort of 10 times the speed of anything else, so you just don't get to see the shape of the graph that's included there. So what was it, 5 million and 5? I don't know, big number. Okay, so just to prove that everything reacts the way that it should, I've looked at what would happen to both the distributed and the replicated store as you add more nodes to the cluster. So this test is based on creating 3 replicas. So it starts with a minimum cluster size of 3, and as the cluster increases in size, it still just creates the 3 replicas, but it's got the whole cluster to go at. And something that I found slightly unexpected is that as the cluster size increases, initially we can see that the throughput also increases before it levels out at just over 8,000. My best reason for why this might be would be that as we're now only writing, or as each write is to a subportion of the nodes in the cluster, any kind of slow nodes or any delays of contention of writing to the cluster or what have you are nullified by the fact that we might not be writing to that node. So, for example, in this cluster, if node 4 is particularly slow, we'll get a much higher throughput every time we don't have to go to node 4. And if we're not going to node 4 very often, that'll raise the throughput. And coincidentally, when we try the same test with the distributed store, we see that the opposite's true. They both start at roughly the same place, but the distributed store drops off and levels out at about 3,800-ish, is it? Something like that. Sorry, replicated, thank you. Replicated store. Yeah, replicated store levels out to about to a slightly lower number, and my reasoning for that is that it's now being dragged at the speed of the slowest node on the network. Every node has to be hit. If one's going at a slower speed than the others for whatever reason, that's included in every single hit. Okay, so to draw some conclusions, both implementations of the object store provide the required throughput. They're both either on a par to the journaling store or faster. And they both provide the availability required that's being tested by failing some transactions and then attempting to recover from a different node but providing it with the same transaction manager ID, and they've been recovered successfully. So the object store isn't tied to any particular physical or virtual machine. And I think that was possibly the entire speed of light. That is pretty much it. If you want to have a look at what I've done, it's on my Git repo, so feel free to pull it down and navigate my reams of uncommented code. It'll be great fun.
You did come across some interesting problems during the you've got time to talk about them.
15. Get the answer to 2 questions.
It might be interesting to talk about those things that came across during the project.
Also, the recovery side of things as well wasn't mentioned at all. Recovery wasn't mentioned at all, but we spent quite a bit of time figuring that out, even though it kind of didn't come to a... it's got a solution, hasn't it? It's not ideal, but...
Well, yeah, recovery doesn't mean that.
Well, I think he needs mentioning mentioned what the difficulties are.
And that's where you found most of the difficulties.
Yeah.
You've got them the 10 minutes. Then,
some really interesting topics that you came across.
I think it's topics like recovery that give you distinction. So I trust it'll be in your thesis, but I think you need to come across in your. Also, bear in mind that your marker is probably the first contact potential your marker will have with this work. So that it's inevitably they're going to be forming a first impression of what you've done. So you want to kind of cover everything. Uncover the main things. You don't want to be leaving something out as big as recovery.
Yeah.
Especially when it's one of the more challenging, challenging parts of your work.
I think you could do some better transition between the sections, because the implementation section is titled in pin span. So, might work sort of spelling out that we're moving from motivation to implementation to benchmarking. I don't usually put like one slide in that says implementation on it, but it might help you. We're moving between the section, and I think that implementation will be a better thing on your agenda rather than within a span will be a better word, or something along the lines of that.
Just a bit of feedback. I thought early on when you were talking about writing to disk, you implied, and it was pretty obvious from that that the performance you were looking to improve upon was because disk writes are expensive, but you didn't actually explicitly spell that out. It might just, for the sake of a few sort of explicit words, there might be worth saying that.
That locate API must take a parameter and must be key. I wanted to say so much, but I didn't want to not go to it looked like it just locate.size could be cluster size. I presume locate takes it.
Yeah, yes it does.
Is that a particular expensive operation?
Yeah. Well, I thought it would be. I thought it would be a phenomenally expensive operation. But when I tested it, it actually wasn't. There is a cost associated with it, but it wasn't sort of the 50% or something.
Probably worth the audit seemed expected to be, and so maybe worth mentioning that.
Not all sales on the street from university.
So it's okay to distribute in core, or is it just using metadata?
I'll just go along and there's
I'm assuming, having seen how much it doesn't slow everything down, I'm assuming it's got to be just the metadata. I mean, it's not. I can't find any explicit details on it in the docs. I just came across it hunting through the API, and the information that I've got about it literally says we'll find every key, or find the location of every key. Of the key.
So those performance figures you showed include the cost of all keys?
Yes. Yeah, what I forgot to mention, it doesn't work on a replicated cache, it just returns one. For some reason on the replicated cache, so when you try and say throw store if not writing more than 3 replicas, it blows up, so the replicated cache figures don't include it, but the distributed cache figure there does.
So that makes it very difficult to compare the distributed keys.
Yes.
One thing I felt was I think you could do with a very quick introduction to what you do before you actually launch into, like the very first slide. Say hi, my name's James. I'm blah blah blah. I'm here to talk to you about my thesis, which is on. And then you've got like a very quick, like 2-sentence summary of what your thesis is. Because when you start talking about the agenda, I don't feel like I know enough about how that agenda applies to what you're going to talk about. See what I mean?
Yeah.
Also, take a look at the numbers on your slides. Some of these slides got like benchmarking 2, benchmarking, and I don't know if benchmarking 1 existed. Yeah, you launched into benchmarking 2, but I presume you've taken out benchmarking 1. Oh, sorry. Did you? Okay. Well, maybe just put a number benchmarking 1. Oh, hang on, Yeah, maybe because this is about the benchmark, isn't it? It owns the benchmark results.
Yeah.
So maybe call it, I don't know, benchmark test or something, or benchmark something, and then benchmark results or something. What you saying, Stuart?
No, I was just wondering, you thought about adding some UML to try and explain what you actually do to the API. So in case like you're calling put, or was it put, or I can't remember. Then you're doing it locate repeatedly to actually to make sure the size is correct. You just feel
Sequence diagram.
Yes, sequence diagram. Just give a feeling to the what's actually happening between an API and the for transaction test list, or at least maybe explain that a bit. If you actually bring in crash recovery, I imagine those interactions are far more rich than.
Yeah. Yes, I have a sequence diagram for the normal case and then one for the recovery case. I think sequence diagrams are quite easy to process and quite easy to describe, aren't they? So. Any more questions or feedback? Tom?
Well, I thought it was great. Did you get my point down that I mentioned conversationally before you did about the titles on the graphs? Did benchmarking 2 and then scale test 3 and benchmarking is that, I think we need to look at the titles.
Yeah, so particularly on the first one, there was something 2.
Yeah, well, I think there was a benchmarking and then a benchmarking.
Something, then something too.
Yeah, but I don't think I'd do that. I'd call it benchmarking and then distribute the store graph and replicate the store graph.
Or benchmark results.
And if you put benchmarking on its own in a slide, when you move to the benchmarking section, then you're in the benchmarking section. So, but yeah, that was great. Thank you.
I think we did a good job when you were doing the background as well early on of keeping us informed of how that linked to what was going to come further on with the research you'd actually done. So I think that's pretty good.
Just to be completely fair, things up some of his mannerisms.
Just to make it really self-conscious.
Yeah, you're not going to prepare for something.
That's good either, is it?
If it's any consolation, when we did a console, they completely rectified.
We all did, didn't we?
Yeah.
I stood like a teapot.
Yeah.
Like this.
I can't remember, so it was a line dance.
Yeah, that's true.
There was somebody who kept going like a hot fire. And there was there was definitely the line dance. We'll give you some tips afterwards.
Did you get weather presenter in there as well?
Sorry?
Did you get weather presenter in there as well?
Yeah. Scotch.
Okay, so I guess is that all the feedback we've got? Everything? Just we're on pieces now, I guess. Yeah. Okay, well, thank you for those watching remotely, and hopefully we'll see you at the next virtual JBug. Bye bye.